MacMaths, let's do some maths today. Okay, so we're on chapter 11 and we're looking at variable acceleration, and this is new to the mechanics with a new course, and we're on chapter 11 like I've just said, and we're looking at ones now that involve integration. So the last ones that we've been doing, we've been moving down this S, V and A line, really, this staircase from displacement, velocity and down to acceleration, and we differentiate when we go down. And so what we're going to be doing, we're going to be looking at problems within this chapter where we integrate. So we integrate the acceleration to get velocity, we integrate the velocity equation in terms of time to get the displacement. I do like these questions, and this is really one area of maths where you're looking at real life situations and and the graphical interpretation of those. So it's you're looking at it with both sort of two sets of eyes, really. So I think it's good for students to see that, and it increases your understanding. And in all cases, I'll point it out as I go through the questions, but I want you to think about sort of both cases. Okay, what we're doing algebraically and graphically, and how that relates to a real life graph. Okay, so let's start this exercise. So we're looking at exercise 11E. So this is the first exercise with integration involved in it. I don't need any more explanation because the other ones have just, I've talked about in the other lessons, going down and differentiating displacement to get velocity and differentiating velocity to get acceleration. So we're just simply going to integrate up. The problem, of course, that integration causes is that it creates when we integrate up, doesn't it? It creates this constant, that will have disappeared on differentiation. And we've got to put that back in. So we always need a coordinate, and these questions will always have some sort of, if you've got to integrate up, they'll always have some sort of coordinate. Okay, so here we go. Question 1, obviously the sort of simplest. Question 1 and 2, really simple. So I'm not going to go through all of these, I'm just going to go through, in fact, the first one that I've sort of written out. So in the exercise 11A, it says a particle is moving along a straight line, given that S is 0 when t is 0. So there's your coordinate. The displacement is 0 at time 0 in the simulation. Find an expression for the displacement for S if v is equal to 3t squared minus 1 is the first one. So v is equal to 3t squared minus 1, that's the velocity. Okay, so what we're going to do is, we know going up we integrate. So if we integrate the velocity with respect to t, we get, so we're going to integrate that and we get an equation for the displacement. So I'm just going to use, rather than use dv and by dt and all of that, I'm just going to actually use the letters now. So we add 1 to the power divided by the new power, so we get t cubed, and that becomes minus t, doesn't it? We've got to put a plus c on the end there, and we've got to find that constant. So when we integrate, creates this constant, doesn't it? But actually on this one here is saying that s equals 0 when t is equal to 0. So there's our coordinate. So if we put s is 0 there and t is 0, we can see that c is also 0. Okay, so the equation for the displacement is just t cubed minus t. Okay, in terms of time. All right, and there's 3 or 4 more of those for you to do, but you just integrate in, putting plus c on the end and putting this coordinate in. Question 2, that was question 1, and question 2 exactly the same thing. This time it's just starting with the acceleration. It's telling you that the acceleration has, there's your variable acceleration, has this formula in terms of time, and it wants you to find the velocity. So we're at this point here, the acceleration, so we need to integrate up to get to the velocity. So if we integrate this, we get an equation for the velocity. Of course, add 1 to the power, t squared, and divide by the new power, divide by 2, 8 divided by 2 is 4. Add 1 to the power, t cubed, and divide by the new power, 3, but we already had a minus 2. Again, that is, have I done that one right there? -2, yeah, 2 cubed. I want the power divided by the new power, and that one is going to stay like that again, because we're going to put a plus c on, but you can see that the velocity is 0 when t is 0. When you put t as 0 into there, the c is going to be 0 as well. Okay, so that constant is 0, and so that just becomes the equation for the velocity. Okay, and again, there's several more of those, and you're just integrating up and putting a plus c on the end and working out that value of plus c. Okay. So what I've done is I've gone through, apart from just doing 1 and 2, which are the easy ones, I've tried to go through a few of the odd numbers. I'll put those on there. I'll do number 3, 5 and 7, and then I've done the last one. The last one always promises, doesn't it, to be the most difficult. So, okay, so let's go through question 3. And again, I've sort of paraphrased the question a little bit. It's a bit more wordy in the textbooks, but I've written it out. So a particle P is moving along the x-axis. At t seconds, its velocity is 8 plus 2t minus 3t squared meters per second. At t is 0, P is at a point where x equals 4. Okay, so it's moved 4 along the x-axis. Find the distance of P from O, O being the origin, when t is 1. Okay, so the first thing that we've got is that we've got that the velocity is equal to 8 plus 2t minus 3t squared. And we've got this coordinate here. At time t, we've got a distance of its travelled in at the start. When t is 0, it's already at 4 meters, from the origin. So s, the displacement, is already 4. So if we integrate this, let's integrate it and get our equation for the displacement. Okay, we get 8t plus t squared minus t cubed, and let's put our plus c on. Now we know that it's already at 4. It's moved along the x-axis from there's the origin, and it's at 4 here at t is equal to 0. Okay, there it is. It's there. So if we put the displacement at 4 when t is 0, okay, we've got 8 0 to 0 plus 0 minus 0 plus c. We can see that c is 4. Okay, so now we know that the displacement is 8t plus t squared minus t cubed plus 4. That's the displacement. Now we can answer the question. It says find the distance of P from O, so where is the point from the origin when t is 1? Well, we've got the equation for the distance, which is displacement, and if we put 1 into there, we get s is equal to 8 plus 1 minus 1 plus 4, so s is 12 units. This question was in, this is when t is 1. Okay, so 12 units or 12 meters if it was in meters, whatever. Okay, all right, that's that one. Again, do put these on pause and have a go at them first, before you see me do them. That's number 3. I've got number 5 there. I have got number 5. There it is. Here we go. Number 5. Put that in. I've done these as well. Did these before. I obviously went through them with you, so I've got them in the sheet sort of next to me here. I do struggle sort of looking, and it puts me off sometimes. But obviously I don't want to get stuck while I'm going through them. And now that I'm 53, my brain has really sort of slowed down over the last few years. I'm probably just about 3 or 4 years from dribbling and talking to strangers in the park. Anyway, here we go. Number 5. So a particle is moving in a straight line. After t seconds, the velocity is, so the velocity is 6t squared minus 51t plus 90 meters per second. When t is 0, s is 0. So there we go, we've got a coordinate, haven't we? So let's just integrate this straight away to find out what that is, and we get, so this is going to be t cubed divided by 3, so it's going to be 2 minus, oh that's awkward, squared over 2 plus 90t, and we've got plus c, haven't we, on the end, but this time t is 0 when s is 0, so when we put 0 into there, that c is going to be 0, so we can just get rid of that straight away, it makes it nice and easy. So there's our equation for the displacement. Find the distance between the 2 points when P is instantaneously at rest. Okay, so yeah, it's a good question, this one. So P is instantaneously at rest. Okay, we'll look at the velocity. Okay, it's at rest when V is 0. Okay, so when the velocity is 0, that's when it's instantaneously at rest. And this is a quadratic. Okay, so if we were to, this is where I want you to start thinking about it graphically as well as in real life. So let's just think about that. There it is. I've drawn a diagram of this quadratic. Now I know it's because the question is implying that it is instantaneously at rest at 2 points. In other words, V, there's your time, velocity time graph. There it is. At those 2 points, the velocity is 0. So what's actually happening here? That it's slowing down, okay, becoming 0, and then the velocity is speeding up, but in the opposite direction. So although it looks like that, what it's actually describing is something going along, slowing down, going back this way, and then stopping, and then going back again the other way. Okay, so that's what's happening. Speeding up in the other direction, slowing down in the other direction, 0, and then changing direction at these 2 points where it goes from a positive velocity to a negative velocity. So it's something, you know, it's like oscillating. Okay, and we're going to find ultimately the distance between those 2 points. Okay, we need to find the times first of all between those 2 points. So if we take the velocity, okay, is equal to 6t squared minus 51t plus 90. Now to find the roots of those equations, we're just putting it equal to 0, aren't we? And when we put that equal to 0, then we're just factorising this, aren't we? Okay, so let's just factorise that. Actually, I'm just looking at that now, and all of that will, I can see that 51 is 17 times 3. So before I factorise it, actually, I'm going to divide everything by 3. The velocity, we want it when it's 0, so put that equal to 0. Divide everything through by 3, and we're going to get 2t squared minus 17t plus 30, and that is going to factorise, and I can see where that is going, especially when I've written it down before, and t minus 6. But you could use the quadratic formula, and you can see t is 2.5 seconds, and t is 6 seconds. So there at 2.5, and there at 6 seconds. Okay. Now this is where it's good to, you know, think about, you know, both situations graphically and algebraically. We can put the we can integrate this between the limits of 6 and 2.5. And remember, when we integrate between the two limits, it finds the area trapped by the graph by just pure mathematics, doesn't it? And this area is going to be a negative area, and that negative area just gives me the distance underneath the graph. So that is what I'm expecting when I put 6 in there to find out where it is at 6 and where it is at 2.5. I'm expecting to find a negative number, but all that negative number reveals is where, you know, it's still the distance, but it's just where that distance is. It's the other side of s equals 0 that you would want. Okay, but it doesn't really matter. So what we're doing is we're just putting 6 into there, okay, to find out where it is, and we're putting 2.5 into there to find out where it is, what's the distance, the displacement, and then finding the distance between the two. And you can do that all in one go on your calculator. So you just put in 2 times 6 cubed in minus 51 times 6 squared over 2 plus 90 lots of 6, and you're taking away with 2.5 in there. Now I did that, okay, and I got S is equal to minus 42.875. That's an indication. It's like just integrating that without sort of doing that. It's indication, isn't it, of the area being the minus being underneath the graph. But the distance, of course, the displacement is just 42.9 sort of meters to 1 decimal place. Okay, by putting 6 and 2 into this equation for displacement. All right. Okay. Hope that one's okay. And we're looking at number 7. 2 more to go. I love this question. Okay, so this is one where I would ask you to sort of think about, and I'll go through this one, think about it algebraically and graphically as well. So a particle is moving along the x-axis again, the velocity is 4t minus t squared. You do have to be careful with this one, and time t is 0, p is at the origin, okay? So again, we can integrate that, if we just sort of integrate, that to get the equation for s, we get 2t squared minus t cubed over 3, and of course that when t is 0, s is 0, so we've got our plus c on, but that's going to be 0, okay, because it'll all cancel out to 0. So we've got our displacement. Now here we go. A, find the value of x, so how far it's travelled, at the instant when t is greater than 0 and p is at rest. Okay. Right, okay, so p is at rest when the velocity is 0. So if we take the equation for the velocity and put it equal to 0, we get 4t minus t squared. Okay, and we need to again find that. Now looking at this here, this is where let's look at what it would look like graphically. Minus t squared, and we know this factorizes to t 4 minus t, doesn't it? It's one of those simpler ones like that. So there it is. The minus t squared tells us that it's a negative quadratic, so it's a sad face, and that t is 0 and t is 4. Okay, so it's at the velocity is 0 at t is 0, and then it sort of speeds up and slows down and changes direction, you know, at t is 4 and becomes a negative. So it's instantaneously at rest here, and it says find the value of x at the instant when t is, how far it is. Well, we know that at t is 0, the displacement is 0, but because it tells that in the question, but it says when t is greater than 0, so it's asking for this particular point here, the time greater than 0 when it's at rest. Okay, and it's at rest here. This is our velocity time graph when t is 4. So if we put 4 into here, we get 2 times 4 squared minus 4 cubed over 3. We get 10 2/3 meters. Put that into your calculator, and that's what you get. Now this is what I like about this question. It says B, the total distance moved by P in the interval between t is 0 and t is 5. So there's 0 and t is 5 is here. Okay, so remember that the area under the graph is the distance moved. Okay, so we know between 0 and 4 it's moved 10 2/3. What is that? That is that distance there, isn't it? Okay, that is that area, sorry, there. if we'd integrated between 0 and 4, put 0 into there and 4 into there and took one away from the other, you would have got 10 and 2/3 integrating between those two limits. So that represents that area. We can't integrate between 0 and 5 because remember, from integration we've got a bit above and a bit below and it will take away 2. So we have to integrate between 5 and 4. Well, we already know what s is at 4, so if we put 5 into here to work out what it is, so if we put 5 in, we get 2 times 5 squared. 5 cubed is 125. I'm going to go straight for that. We get s is 8 1/3. That gives us 8 1/3 meters. Okay. So at this point, you've got the displacement is 8 1/3 meters. Now the displacement is where it is from the origin, the x-axis. There you go. Okay. So what it's done is, in 4 seconds, let's think about this, it's moved 10 2/3 meters, okay, to that point there at 4 seconds. Then the velocity stops, and then the velocity goes negative, so it starts to come back. And remember, this is not the distance travelled, s is the displacement, the distance from the starting point. So now it's at the 8, this is 10 2/3, let's put that there, that distance there. Now it's at the 8 1/3 point. Okay, so how far has it travelled? The question is not displacement, it is distance, the total distance travelled between 0 and 5 seconds. Well, between 0 and 5 seconds, it's travelled 10 2/3 of a metre. You can't take that away from it, it's travelled that. And then it's travelled back that short distance from 10 2/3 metres away from the origin to a displacement of 8 1/3. So we need to do that plus that bit there. And that bit there, of course, is 10 2/3 minus the 8 1/3. That's that bit there, because 8 1/3 is the distance from the origin, the displacement. Okay, and that take away that, you can see, is 2 1/3 meters. So it's travelled 10 2/3 meters to there, and then it's travelled 2 1/3 meter back. That's the minus velocity in the opposite direction. So the total distance, not displacement, distance, which is what the question is asking, is 10 2/3 plus the 2 1/3, which is 13 meters. Good question, love it. Okay, so think about how you would do that, you know, by integration. That is what you're doing. You're finding the area between 0 and 5, aren't you? The total area. But you couldn't just integrate between those two limits. You'd have to integrate there and get that area, and then you'd have to integrate between those two and get that area. It would come out as a negative area. It would come out as minus 2 1/3 to indicate it's below, and then you ignore the minus because it's just a distance travelled, isn't it? So, or it's just an area. So you'd add the 2 1/3 to the 10 2/3 that you got, okay, to give you a total area of 13 meters, which is the total distance travelled. Okay, that's number 7. It's a good question, that one. Okay, and this one here, I think this one is a bit easier. Number 12. I think it was fairly sort of straightforward. Oh no, not so straightforward, but good fun still. You could do a shortcut for this by doing B first, actually. But let's pretend we haven't seen B and let's just do A, because it makes it sort of more fun. A particle travels on a straight line such that A is, so the acceleration is 6t plus 2. And then it talks about the displacement, okay, and it gives you 2 coordinates. Now, it's giving you 2 coordinates and it's asking for the displacement when t is 4, okay? So we need a formula for the displacement s, and we've got a formula for acceleration. So that means we've got to actually integrate twice. We've got to move 2 steps up our ladder here. And every time we move up a step, of course, we've got to add on a constant. So by the time we get to the top of our ladder, we're going to add 2 constants onto that, aren't we? Okay. So let's integrate that up to, that's meant to be my integrate sign, to the velocity. And when I integrate that up to the velocity, I get 3t squared plus 2t plus a c. That's my my constant. And let's integrate it up again to s. I'm going up this ladder, integrating up, and I get, that's going to be handy, isn't it, t cubed over 3, so it's just going to be t cubed squared, so you can see what I've done there, plus ct plus another, so that's just a number, isn't it, so that has a t on the end, plus a second constant, which is d. Okay, so there is my equation for displacement, and it's got 2 unknowns in it, unfortunately, c and d. There's 2 constants in it, but we've got 2 coordinates, so that's okay. So we can put the first coordinate in of 10 meters when t is 3. So if we put 10 in when t is 3, oh no, sorry, 10 when t is 2, okay? So s is 10 when t is 2, that's the first coordinate. So we get 8 plus 4 plus 2c plus d. And if we simplify all of that, you can see that we just get minus 2. Adding that together, taking it off both sides, is equal to 2c plus d. So that gives us one equation. Okay. We can also put in the equation, I hope this is going to fit in, of, where is it now, s is 38 when t is 3. So putting it into there, we get 38 is equal to 3 cubed, which is 27, plus 3 squared, which is 9, plus 3c plus a d. And simplifying all of that, we get, add that together, take it off there, that comes 36, so you take it off, you get 2 is equal to 3c plus d. Okay? So now we've got those 2 equations from those 2 coordinates, and we can just solve that simultaneously. And I'm actually just going to, because I've got a d and a d, I'm just going to line them up by elimination. They're really, you know, grade C GCSE, and 2 is equal to 3c plus d. There we go. And I'm going to take away minus 2, take away 2 is minus 4, 2c, so it's minus c, and that goes, so c is equal to 4. And if c is equal to 4, 3 4s are 12, take it off, so d is minus 10. Okay, so now we've got the equation, here it is, displacement, and we've got s is equal to t cubed plus t squared plus 4t minus 10, there it is. And I've put in the c and the d. And now all I have to do for a is put in t is equal to 4. Find the displacement when t is equal to 4. So I just need to put 4 into there. So when t is equal to 4, you get 4 cubed, which is 64, plus 4 squared, which is 16, plus 4 fours is another 16, minus 10. S is equal to 86 meters. Okay. And it also wants the velocity when t is 4. So there's the velocity. Okay, and we know that that c, this is for b, we know that that c was 4, don't we? We worked that out. So the velocity, the formula for the velocity is 3t squared plus 2t plus 4. That fits on to my screen. I'm just standing up to have a little look. Oh, just on. Okay, and so if we put what am I doing? I'm putting t is 4 into there, aren't I? So let's put a box around that, because I put a nice little box around that one. So v is equal to, what am I, 4 squared 4 squared is 16, so that's 48 plus 2 4s are 8 plus 4. So the velocity is equal to 60 meters per second to the minus 1. That's not going to fit on, is it? You can just see it there, right at the bottom of the screen. So 60 meters per second. Okay, to the minus 1, the velocity. Okay, and that's number 12. So have a go at those other ones. Message me if you get stuck on any of those, and I'll do a little vid for you and attach it to show my own work for you. But do those ones first. 1, 2, 3, 5, 7 and 12, and you should be able to do the other ones in between. Okay, think about them all graphically, what's happening, you know, relate it to your knowledge of integration and finding areas under curves as well. And it should all start to tie together and improve your understanding of the maths and how it applies to the real world. Okay, all right, over and out, guys.